So, hello everyone, my name is Eduardo. Today I'm going to present you my thesis subject called Multi-Source Domain Adaptation through Wasserstein Barycenters. My name is Eduardo. This thesis is directed by Antoine SOULOUMIAC and it's supervised by NGOLE. So, I divided this presentation into 5 parts. Brief introduction about the subject that we treat here. Then I'm going to talk about the theoretical background of this thesis called optimal transport. Talk a little bit about our methodological contributions. Talk a little bit also about the applications of this thesis, mainly cross-domain flow diagnosis. Then I'm going to finish with a bird's-eye view of our contributions, as well as the perspectives that we got at the end. Now, for the introduction. This thesis is, at its bottom, about machine learning. In this presentation, I'm going to focus on the case of classification. Usually, when you want a machine learning model to classify images, for instance, you collect a comprehensive enough data set, you feed it to a learning algorithm, and it gives you a general rule. Now, here I'm illustrating the case where you represent complex images through features. In this case, for simplicity, I put them on the plane. So if you do everything well, and you want to classify, for instance, 2 classes, here backpacks and laptops, these 2 different kinds of objects are mapped in different parts of space in the feature space. So you see the triangles that represents the backpacks, the circles that represent the laptop, and your general rule is a function that separates these 2 classes. Now, desirably, what you want is to get a new sample in the far right of the screen that was not present in your training dataset, and hopefully it gets mapped on the right part of the space that it allows your general rule, in other words, your classifier, to predict it correctly. You're generalizing because you have not seen this sample before, and you're predicting it right. Now, somewhere here, we're going from finite samples to an infinite thing. There is a function that's defined over the whole feature space. This is called the machine learning generalization. It's the holy grail of machine learning. But the problem is, oftentimes, machine learning systems are required to work well on data that does not quite look the same as your training data set. This is called domain adaptation. So here I'm showing you an example where I have images of laptops and backpacks that vary in terms of style, background, pose, and illumination. Now, when you look at the features of these different kinds of, let's say, domains, you see that they appear different in different parts of the space. If you give a probabilistic foreground to how you understand this thing, you begin saying that the data follows different probability distributions. That is, the feature points are likely to appear in different parts of space. Now, the problem is, of course, if you see the general rule, that is your line age, it's not going to predict well on the distributional shift. This is the problematic of domain adaptation. Now, what do we want in this thesis, as you see by the title, is to design new algorithms for domain adaptation. The part where this thesis is effectively different is that we deal with multi-source domain adaptation. So in a nutshell, we don't have only one single source. We actually have many, each one with its own distribution. And we need to adapt to a 4th one, called the target, here in orange. And, well, the whole challenge is everything changes between the multiple distributions. Now, the question that now comes is, how are we going to design these new algorithms? And we're going to do it through optimal transport. So to motivate optimal transport, I picked a personal example from my hometown of Fortaleza. So here you see the map of Fortaleza, and you have fish markets and restaurants. The fish markets want to sell fish to the restaurants, and imagine that you yourself is like the manager of the city, let's say, and you want to allocate, do this transportation at low cost, at the lowest cost possible. So here we're gonna model the demands of the restaurants by these little QJs, and the offer of the fish markets by the little PIs. For simplicity, we're gonna assume that we have the same offer as the demand. Now, you may try to solve this in a greedy way. What does that mean? For instance, each fish market picks its nearest neighbor and sells everything to this restaurant. If you do that, you see the optimal strategy in the map on your right, and it costs 5.6 euros. Here I'm assuming that each kilometer that you travel, you expend 1 euro. Now, the other way around corresponds to pick everybody up, tell everybody, well, we're gonna try to solve a problem, and this problem is gonna be better for everyone. This problem is the optimal transportation problem. You have your variables that is who sells how much to who. It's your gamma ij's, and you have the travel distance that's weighted by how much mass is transported from one place to another. Now, the interesting thing about this problem is a linear program, and if you solve it in this particular case, you get 4.8 euros. You notice that is less than the first one, because it is the optimal way of transporting mass in these kinds of conditions. So what I just did is I gave you an economical interpretation or motivation for the optimal transportation problem. Now, you may note that this is about machine learning, so we're gonna give a probabilistic background for these ideas. Now, if you translate one thing into another, we're not going to begin talking about probability distributions. So you have a source probability distribution here in blue, and you have a target probability distribution here in red. Now, your optimal transportation problem is going to correspond to transports of mass, that is probability mass, from one place to the other. So in this case, you have an analogous infinite dimensional linear program that corresponds to the optimal transport plan, here denoted by gamma. The interesting thing is, just as in the economics problem, you have a cost associated with optimal transport. Under certain conditions, this cost corresponds to a metric in the space of probability distributions, called the Wasserstein distance. There are actually many different probability metrics, that is, ways of computing differences between probability distributions. And the thing about the Wasserstein distance is you begin matching these masses between the two distributions, and you begin computing differences between these distributions horizontally. This is very different for when you see, for instance, F divergences, where you compute a ratio between the densities. That is, you compute these distances vertically rather than horizontally. Before proceeding, I'm going to make a slight turn, because I'm going to talk about how to solve optimal transport with a computer. So far, we've been considering optimal transport as an infinite dimensional problem. Now, in this thesis, we focus mainly on 3 different kinds of approximations for the true density of the data, let's say. The first one is it's a simple idea. You sample from your distribution, you get, let's say, n samples, and you put a direct measure, a direct distribution on each one of these samples. And then you consider a mixture of these directs. The second one, you approximate the distribution by a Gaussian. And the third one, which is quite more flexible than the second, you estimate a Gaussian mixture model. That is, you have a set of means and covariances. Now, the idea is that from the first one to the second, we make a rather strong hypothesis. That is, we make the hypothesis that the data is Gaussian. In the third case, we are actually, we have much more flexibility because we have more parameters. So, when we go to the empirical case, we have, much like the economics problem, we have a linear program between your source distribution samples, and your target distribution samples. Here, denoted by the blue area and the orange area. You also have a way to compute the Wasserstein distance between these sets of points. Furthermore, sometimes you may want a mapping between these two, let's say, point clouds. Even though it may, an optimal transport mapping may not always exist in this case, you have an approximation for it called the barycentric mapping, which is a formula that depends on the optimal transportation plan. If you want to solve that, you have to pay the price of solving a linear program, that is n cubed log n. That is, it scales with the number of samples. So if you have a huge data set of samples, it may take a long time. Now, if you assume that your data is Gaussian, funny thing happens. Optimal transport has a closed form solution. In this case, it takes the form as the difference between the means plus a term accounting for the distance between the covariance matrices. The idea is that you can estimate from your samples the parameters of these Gaussians, and then you can compute the distances. But beware, in this case, you end up paying a cubic complexity with respect to the dimension, which, if you are in high dimensions, it may not always be possible. And you also have to deal with the challenges of inversions and calculating the square root of covariance matrices. Now, if you pass up to the Gaussian mixture model, through optimal transport between Gaussian mixture models, and you make an additional assumption that the optimal transport plane itself must be a Gaussian mixture, there are a series of intriguing results that establishes a connection between the continuous problem and a discrete problem between the components of the Gaussian mixtures. So here I'm denoting by omega this optimal transport plane between the components of the Gaussian mixture models. Associated with, let's say, this variant of the Wasserstein distance, you have the mixture Wasserstein distance, which defines a metric in the space of GMMs. Now, a funny thing happens here, as I said, is that you are solving a far smaller optimal transportation problem in the number of Gaussian mixture components that you have. So here I denoted that by k. It's k cubed times log k. Now, just to stress the reduction in the computational burden, you have your samples in the first layer, and then you compute the, let's say, the means of the Gaussian mixture model. Effectively, what you are doing is you are clustering your samples into the components. So the idea is that you are reducing the number of things that you are computing optimal transport on. And of course, since the optimal transport is a Gaussian mixture model itself, you have two layers of optimal transport plans. Sorry. You have a bottom layer where you have a plane between samples, and you have an upper layer where you have optimal transport, an optimal transport plane between components. Now, with everything that I talked about, you define effectively a notion of barycenter, a notion of distance in the space of probability metrics. If you have a notion of distance, you can define, by analogy, a barycenter for probability distributions. In some way, you want to average a family of distributions, and you do that in analogy with the Euclidean case. So you have that minimization problem on the far right of the screen, sorry, in your far left. And by the way, associated with this family of distributions, you also have a whole family of possible distributions that you parameterize based on the weights that you assign to each distribution in the family P calligraphic here. So in the following, I'm going to explore the barycenter itself. That is, I may refer to the barycenter when I use uniform weights, as well as the interpolation space associated with this family of probability measures. I gave you a figure illustrating this here, where you have your groups of points grouped in terms of color. And then you have an upper layer of abstraction, where you have each one of these groups of points encoded into a distribution space that is here called the Wasserstein space. Now, with that, we can calculate the barycenters, and here I give you 3 examples, 2 of them calculated with the so-called maximum mean discrepancy, and a third one that is the Wasserstein barycenter. You see 3 different things, and you may be asking yourself, well, which one is the better for computing a barycenter? The answer is, it actually depends on what you're trying to do. For instance, if you're doing domain adaptation, you might want to have a barycenter that better captures the intrinsic geometry of the data. If you are doing generative modeling, on the other hand, that may be valid, but sometimes you may want a notion of barycenter that combines the sample of the 4 of them. In this case, the MMD with a Gaussian kernel might be better. But this is just to exemplify the nuance that when you choose a metric, you're actually choosing a geometry for this rather complicated space, that is the space of probability measures. Now, I'm going to start talking about the contributions that we did in this thesis. But before presenting the first one, I'm going to just talk about the first method for doing domain adaptation using optimal transport. So you start at the far left with your source and target samples. Here they are denoted by circles of different colors and triangles of different colors. The colors encode the class, and the shape of the points encode the domain. Your target domain are the triangles. If you fit a classifier with your source data, as you can see on A, it will not, on B, sorry, it will not work on your target data. This is because there is a distributional shift, and as I said in the beginning, you have the samples, they appear in different regions of space. Now, on C, you have your desired case where you fit a classifier on the target itself, but this may not be possible because you don't have labeled samples on the target domain. A way of solving this is computing the optimal transport plan between the distributions that gives you the figure on D, which matches each point on the source with possibly many points on your target. Now, based on this matching, you can transport the points in a straight line towards the target, and they are going to carry the labels. With the carried labels and the points themselves, you can fit a classifier on the target on E, here shown on figure E. Now, I'm going to call this method OTDA, and it's going to be the, one of the parts on the components of a contribution of ours. Now, a challenge that comes with doing that is that, at least in the work that I presented, the authors did not consider distance between labels, or at least not in the original optimal transportation problem. Now, we can ourselves add a term using the labels, but now a question comes, and it's a pivotal question that's still open: how to encode the labels so that the encodings of the label get the geometrical properties of the classes. Here we chose to use one-hot encoded labels because that nicely translates into a strategy for interpolating the labels of the distributions. This is given by the label propagation term that we add to the barycentric mapping that effectively transports the one-hot encoded labels via a convex combination. Now, we added this term. Now, this defines a metric on the joint space of features and labels. And now we can begin computing barycenters of label distributions. So this is what's shown here. You have your multiple sources on the far left. You compute the joint Wasserstein Barycenter, that is joint between features and labels. You get the distribution on the middle, that's the barycentric distribution. Of course, not necessarily this resembles the target, so you do an OTDA step for matching the barycentric distribution with the target one. Now, we compared that with other methods in the state of the art, and we saw that it worked quite well. Now, a question arrives. If you're computing the barycenter, you're not forced to use uniform weights. So we begin looking at how to find in the space of interpolations the barycentric distribution that most resembles the target. This is what is called barycentric coordinates regression that was previously used in the context of histograms, and now we adapt in our works to do that with point clouds, distributions of free support. Now, of course, this involves computing a different kind of barycenter. There is a Wasserstein Barycenter, but with a different machinery behind. In this thesis, we wrote that as a projected gradient descent algorithm. Basically, we evaluate the Wasserstein distance of the barycenter with the barycentric coordinates with respect to the target. And then we compute the gradient, we take a step, then we project back into the simplex. Now, without moving that to the target domain, we tested with respect to the other methods, and we saw that, well, it may not work as well. This means that, in most cases, the target domain actually does not belong to the space of interpolations of the sources. Now, a question comes from that is, how can we include the target into this space of interpolations? Now, I'm going to present you another solution with dictionary learning that actually includes the target into this space of interpolations. So, just to present what actually is dictionary learning. Originally, it was proposed for expressing a set of vectors as the product of a matrix of representations, here denoted by lambda, times a tiny dictionary, that is a few vectors that encode the complexity of your data points. Now, I'm going to refer to the lambdas as sometimes representation or coordinates, depending on the context. It will be clear in a moment. The matrix P here is going to be the dictionary, effectively. Now, note that I'm representing the data linearly because I'm decomposing the matrix of samples X as the product of lambda by P. There is a problem that exemplifies this very well. It's the problem of PCA. In this case, we're computing the Euclidean distance, here the Frobenius norm between the data and its reconstruction, and we can identify the dictionary as the set of eigenvalues selected by PCA. The representations themselves are the projection of the data into the lower dimensional space. So this is just to give you an example of dictionary learning. Now, what we want effectively is a dictionary learning problem that considers probability distributions. This was previously considered in this paper, Wasserstein Dictionary Learning, as a problem for learning a set of atoms that represented the histograms through the Wasserstein metric. Now, you may see again the same pattern appearing. You have a problem that was defined in terms of histograms. But what we in this thesis proposed was a machinery that allows us to adapt these ideas to free support measures. Now, to go from histograms effectively to distributions with free support. We just need to change how we compute Wasserstein Barycenters. So the problem in itself keeps its form while the object changes. So here I give you an illustration of how we're doing these ideas. You have your set of atoms, that is the P1, P2, P3. There are the vertices in this very complicated space of probability distributions. And then each one of the data sets that you have, each one of the domains is going to be a point inside the space of interpolations of these atoms. We do that by minimizing a term with respect to the target and a combination of terms with respect to the sources. Now, note that we do not have the labels on the target, so we cannot compute a joint Wasserstein distance on the target. While this does not poses a problem with respect the optimization problem itself, the fact that the atoms are labeled afterwards allows us to reconstruct a representation, a reconstruction that is labeled itself. Now, I'm going to move to the optimization algorithm that it's basically, minimizing these loss with respect to each one of these variables, that is the samples and the barycentric coordinates, by taking gradient steps and then projecting back the barycentric coordinates into the simplex. Now, a question comes with that is how can we scale with respect to the size of the data sets? Imagine that you have 1 million samples on your source domains. How can we effectively scale these calculations? We do so through mini batching. And we actually show in the thesis, in one of our examples, that doing so is actually better than considering the whole data sets. But then, if you're doing mini batches, you have other challenges that come around. I'm not going to the details of why that happens, but you basically have an optimal transportation problem that is suboptimal because your transport plan needs to match the points within the mini match. While if you consider the whole data set, you may have chosen other samples to do it. So you begin complicating the optimal transportation overall, but you end up with something that's more scalable and that overall yields better atoms than the full batch case. Now, as I said to you, associated with the dictionary, you have labeled distributions. That is, each one of the atoms is labeled. This allows us to calculate a labeled reconstruction for the target domain. With this labeled reconstruction, we can fit a classifier to the data because we have the pairs of features and labels. This is called the dir R. The other option is to fit a classifier in each one of the atoms, that is, again, a label distribution itself, and then predict on the target, and afterwards, weighting each one of the target classifiers via its barycentric coordinates. We call this the dir E for ensembling. So you have a reconstruction approach and you have an assembling approach. And actually in the paper and on the thesis, we did a bit of theory for proving that these algorithms have a bound that allows us to, we did a bit of theory proving a bound for the error of classifiers fit with the barycentric distribution as well as the atomic ones, let's say like that. So up to now, we're considering empirical distributions, right? We're representing these distributions through their samples. We now move, we tested these methods with respect to the current state of the art, and we actually showed that by doing the dictionary learning step, we actually managed to improve quite a bit in some benchmarks the performance of domain adaptation. Now, as I said, we're using empirical measures. We now want something that's more scalable without using mini batches. The way we did that is through Gaussian mixture models. Now, there is a twist here, because we need to consider a classification problem. We need to consider that we're doing classification. The way that we found to represent feature labeled joint distributions was to label the components of the GMMs themselves. We do that by fitting a GMM to each one of the classes. So we are effectively modeling each P of X given Y as a GMM independent of the others. Afterwards, we can still concatenate every single component of the GMM, and we can attribute one hot encoded label vector to each one of the components. That way, we get a pair of weight, mean, covariance, and label for each one of the components of the GMM. This is what's shown on your left, where you have two classes, and you have each one of the GMMs acquired with them. And of course, you can afterwards do a maximum a posteriori estimation for acquiring a classifier out of your GMM. This basically boils down to estimating from which cluster the data pointer comes, and then attributing the label of this component. Now you may also notice that here we're using axis-aligned GMMs, Gaussian components, that is Gaussian components with diagonal covariances. Why do you do that? Because we're actually doing high-dimensional calculations, and if we use entire covariance matrices, first, the computational complexity is prohibitive, and second, you end up with quite complicated numerical stability problems. So we do these two modeling steps. After that, like the empirical case, we need to consider the labels of the GMM components. We do that in the same way that we did before. We add a term with the one hot encoded labels. Now, when we try to minimize this now called joint mixture Wasserstein distance, we actually find how to map the components of the GMMs with barycentric mappings. So essentially, you have one barycentric mapping for the means, you have one barycentric mapping for the standard deviations, and you have one barycentric mapping for the labels. With these barycentric mappings, we can adapt previous algorithms used for computing barycenters of empirical measures for doing that for Gaussian mixture models. These, again, I'll not go over the details, but it proves, this algorithm proves to be more effective than doing multi-marginal optimal transport, which involves a very, very long linear program. Now, we can adapt our previous algorithms to this framework. First, we have the Wasserstein Barycenter transport algorithm that first computes a barycenter, then maps the barycenter to the target. But now, instead of doing that with samples, we do that with the Gaussian mixture model components. The second one is GMM-Dadil, where we now express each one of the atoms and the source and the target domains as GMMs, and the optimization problem is written now in terms of the Gaussian mixture model components. Now, as I said in the beginning, you have much less components than you have samples themselves. Now, when we compare this to all of the other methods, we get effectively faster because we're not using mini batches. We get lighter because we're using less parameters, and we get better because we effectively push the performance forward in terms of classification, domain adaptation performance, sorry. Now, I'm going to move over the applications. This concludes the part where I talked about some of the contributions of this thesis. So to talk about the applications, one of the applications that we considered in this thesis was cross-domain fault diagnosis. Now, what does this mean? It's basically a domain adaptation problem for the problem of fault diagnosis. In this case, let's say that you have a chemical plant carrying a reaction A that becomes B. Well, you may have another reaction that's close by the first one, but it's not quite the same because now, for instance, you have 2A that becomes B. Now, if you collect signals from the first one, that is, you measure over time x1, x2, x3, x4, and then you try to classify which fault has occurred, you may have a difficult time because of distributional shift for adapting towards the target. Now, this poses effectively a problem of domain adaptation in an industrial case. Now, in our works, what we did was to propose a new benchmark for doing that, and we considered a well-known benchmark in the chemical engineering community. This is called Tennessee Eastman process. It's actually a large-scale process that you can simulate. It carries over 4 reactions where you have 2 products, here G, J, and H. And the challenge here is that you have 6 different modes of production. That, for instance, you can vary the ratio of G and H into different values, and all of that gives you data that follows different probability distributions. Now, I'm stating this because it's the conclusion of this paper, but we actually have to prove it. Now, the good thing about this benchmark, we got all of the simulations, did a bunch of pre-processing, and then we published the data on Kaggle, the pre-processed data on Kaggle, and the code is hosted on GitHub for reproducing all of our experiments. Now, as I said, the different simulations are grouped into different modes of operation. To effectively test our hypothesis that the different modes of operation are associated with different distributions, we computed the pairwise Wasserstein distances between pairs of modes. Of course, we did not use the empirical Wasserstein distance because the number of samples is prohibitive, as well as issues with the curse of dimensionality. We actually did use the Gaussian assumption. Now, as you may see on your left, you have the pairwise distances, but to visualize it, the possible resemblance between the different modes, we did a metric embedding in R2. You have 2 modes 3 and 6 that are similar to each other, and then you have another cluster of 1, 4, and 5, and mode 2 that is very different from the other. Now, in domain adaptation theory, what we can expect is that, for instance, if you take data from mode 1 and you fit a classifier with it, when you apply it to mode 2, it will likely not work. We did a bunch of experiments with various possible cases, and for instance, we define the source only baseline as, for instance, taking data from one mode and testing on the target, or taking data from all of the modes except the target and apply it on the target afterwards. So, for instance, if you compare the performance of the source only classifiers with the target only, we have quite a gap between all of the cases, showing that adaptation towards this mode is effectively much more hard. Now, what we did also was to compare 11 different methods from the state of the art, where we show effectively that our proposed methods in this thesis work very well, even surpassing most of them. And even approaching the target-only case, where I said before, it's a rather optimistic case where you don't have distributional shift. Of course, since we're doing unsupervised domain adaptation, that is, we have no labeled samples on the target, we still have a little gap in performance, but we get quite close to this optimistic case. Now, I'm now going to shift to a study of the interpolation space of the dictionaries that we learn. I'm going to begin with analyzing the interpolations with respect to the Wasserstein distance. The first case, so in here you have 3 domains that are adapted towards a fourth target one. Of course, if you're interpolating between three domains, you have three variables because, you have a representation in R2 because the third variable is defined by the first two. You have a constraint that it sums to 1. Now, if you analyze the level curves with respect to the Wasserstein distance, you see a quadratic pattern. If you do the transportation step towards the target, what you have is essentially noise. Maybe difficult to see, but you have a shrinkage with respect to the range of the Wasserstein distances. It means that we effectively are minimizing the Wasserstein distance, but when you look at the accuracy, you still have a suboptimal performance because you're doing a two-step method. Now, when you do dataset dictionary learning, I'm going to go back, you have the same pattern as the sources, and you have a much nicer interpolation space than the Wasserstein Barycenter transport case. Now, I'm going to move over the Gaussian mixture model case. We start with the mixture Wasserstein distance, which has a similar pattern than the Wasserstein distance. Now, the main difference is that all of the vertices are Gaussian mixture models. If you look at the if you look at the negative log likelihood, the interpolation of the sources is quite complicated with respect to the interpolation of the atoms, which is quadratic as the mixture Wasserstein distance. Now, in our view, this is quite astonishing because we did not directly optimize, either considered the negative log likelihood of the interpolations with respect to the target. We actually have a nicer level curve that is quadratic in this case by optimizing just the mixture Wasserstein distance. Now, if you look at the interpolation curves, if you do the interpolations of the sources, and even if you move it to the target, you have quite a huge gap with respect to the solution with dataset dictionary learning. For instance, the maximum with GMM WBT is 26% less than the one with GMM DADIL. You can also exemplify that by computing the density of the accuracies over this interpolation space. Here we did that with kernel density estimation, and you see that DADIL and GMM DADIL are all over the best performances. You can even zoom in, and you can see that GMM DADIL gets better than DADIL due to the Gaussian mixture model modeling. Just to conclude with the perspectives, we did overall 12 papers. Most of these papers are on multi-source domain adaptation. We also did a review paper on optimal transport for machine learning as a whole. We worked, as I said, in cross-domain fault diagnosis and a little bit on federated domain adaptation. To give an overall of the open questions of this thesis, we have, as I said, the label embeddings, that is, how can we encode the labels to get a better geometric view on the classes, the statistical complexity of especially doing the GMM modeling. In the case of federated learning, if our algorithms respect differential privacy, and generative modeling, which comes especially by using the GMM modeling. Then, of course, to fit this presentation into 45 minutes, I have to left some of our works out, especially those with dataset distillation, federated domain adaptation, and online domain adaptation. Now I conclude this presentation. Thank you very much for your attention.